It is a pleasure to welcome you to the fourth edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP Lecture Series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The Pan IIT Lecture Series on geotechnical engineering is consisting of 6 talks, which have been delivered by the pioneers in the field of geotechnical engineering from different IITs. The following lecture is the first talk of the session 2 of the lecture series. This lecture is on a sampling statistics coupled methods for reliability analysis and global sensitivity analysis, GSA, of rock tunnels, which will be delivered by Dr. Gaurav Tiwari. Dr. Gaurav Tiwari currently works as an assistant professor of geotechnical engineering at IIT Kanpur. He obtained his PhD in geotechnical engineering from the Indian Institute of Science, Bangalore with the Leonards Award for Outstanding Thesis. He has completed his M.Tech from Indian Institute of Technology, Roorkee and B.E. from Government Engineering College, Georgia with Honours Division. Gaurav's research interests are in the arenas of probabilistic analysis of rock structures, characterization of uncertainties in rock properties, dynamic behavior of rock mass and possibilistic methods to analyze the stability of rock structures. Outcomes of his research have been summarized in 30+ technical articles in top-tier international journals and conferences. As a practicing engineer, Gaurav has worked on several projects pertaining to rock engineering projects of national importance including Chenab Railway Bridge and Deccan Gold Mines.
I am Dr. Gaurav Tiwari. I am working as an assistant professor in the Department of Civil Engineering, IIT Kanpur. And today I will be briefly talking about the current research we are doing here in IIT Kanpur on resampling statistics coupled methods for reliability analysis and global sensitivity analysis of rock tunnels. So my student Akshay is actually working on this problem of limited data availability in rock engineering and how to overcome this limitation of the data, insufficient amount of data while analyzing the structures, stability of structures and design of stabilization measures for rock engineering projects. So, I mean, there have been many other techniques like Bayesian techniques on which he is currently working. My other student, Surbhi, is also working on non-probabilistic method, but this is one of the most simplest techniques which we can actually use to overcome the limitations associated with the data insufficiency while dealing with the stability analysis and design of the stabilization measures for rock structures. So with this, let me start my presentation. As a geotechnical engineer, we basically deal with the two natural geomaterials, and the properties of these natural geomaterials are not in our hands. So basically, we have to deal with natural materials. So that is the biggest problem associated with our profession. So when we try to classify geomaterials, we can basically have two major geomaterials which we have to deal with, rocks and soils actually, and both are particulate materials with the mineral grains and voids along them. And along the voids, there can be air, there can be some fluid, there can be liquid. And the only difference, the major difference which we can say is there between rocks and soil are the forces, the bonding forces in between the mineral grain, which is much higher in the rocks as compared to the soils. And soils are basically formed due to the mechanical and chemical weathering of the rocks themselves. So the basic idea of this particular slide was that we have to deal with natural materials. So either if we are dealing with rocks, and either we have to deal with soil. And if we are dealing with natural materials, so obviously we cannot ignore the uncertainties associated with them, because the properties of the materials is not in our hand. So as a geotechnical engineer, we basically, and in particular, if we are dealing with rock engineering projects, we have to deal with the problems associated with the rock slopes, tunnels, foundations, foundation over slopes, and many other problems are there which we have to deal with. But these are some of the examples in which we have to deal with the rock mass at the site. Rock, intuitively saying that when we are talking about soils and rock is a stronger material. Intuitively, we can say that. However, the problem associated with the rock engineering is the presence of discontinuities along the rock. Okay. And due to the presence of these discontinuities, this whole assembly of discontinuity and the intact rock in between, this whole assembly is actually known as rock mass. And this whole rock mass on which we have to construct our structures becomes less strong, more deformable. There will be anisotropic behavior shown due to the presence of discontinuities. And due to the random distribution of these discontinuities along the rock mass, there could be heterogeneity. The scale dependency in the properties comes into picture, and the behavior also becomes time dependent, as we see in the direct shear test when we perform our test under different strain rates or displacement rates. When we try to design any rock structure, basically we have to deal with certain steps. So there can be some specific steps associated with a particular project, but in general, these are the steps which we generally follow when we are constructing any rock structure. So initially, we have to do some geological and topographical investigation at the site. Then we have to do some field observations and measurements at the site, which consist of intact rock characteristics, joint characteristics, joint mean discontinuities characteristics, so roughness, JCS, and all those things, density and pattern of joints, uh, ground details, which includes stresses and groundwater table, and some project related features, which means that what type of project we are dealing with. We are dealing with slopes, either we are dealing with tunnels. And based on all of these, we can actually give some rating to these individual parameters. Okay. And based on the ground condition and the project related information and these characteristics, we can find out that what could be the possible failure mode along the rock structure. So suppose if we are talking about rock slopes, there can be different failure modes like planar failure mode, wedge failure mode, and stress control circular failures. So based on this information, we can have some preliminary idea that what type of failure our rock structure can have. And this can happen in tunnels also, where we have wedge failures, we have continuum type of shear failures. All these preliminary investigation or all this preliminary analysis can be done on the basis of this investigation. Once we get the information related to all of these parameters, we have classification systems like RMR, GSI, and all, through which we can estimate the properties based on the empirical relations based on the basis of these classification systems. And we can then carry over to have the analysis based on the classification system ratings, through which we can find out the properties. Once we get all of these, we can have stability analysis and support estimates. So whatever design process we are actually following, we have to find out different properties or different characteristics associated with the intact rock, joint characteristics, density, stresses, any parameter, any input parameter which will require, we have to measure it, we have to estimate in the field. So the most ideal condition could be that whatever parameters or whatever properties of the rock mass we are actually estimating in the field are precise values, are deterministic values, and they have a fixed value. Okay. So if we have some mathematical model to analyze our structure, suppose for the tunnel, if I am doing some analysis using some finite element code or finite difference method or convergence confinement method or any other method, so it requires some of the input parameters. So if we have some precise or fixed value of that input parameter, then we have to just input that value of the input parameter in the mathematical model, and we can get that what is the output response of the structure which we have to deal with. So this is what is being given here. So suppose if we want to have this elastic modulus of the intact rock from the side. So the basic idea which I want to give you through this slide is that if we get a fixed value of this elastic modulus or precise value of this elastic modulus, then we have to input some simple deterministic parameter in the mathematical model to get the output response of the tunnel, for example, in this particular example for the tunnel. However, ideal case is rarely present in the rock engineering. So the thing is that we are basically we have to basically deal with the unpredictability while estimating the input rock parameters. And unpredictability actually tells you about all our deficiencies and inabilities to be able to precisely predict the value of a particular parameter. So the ideal case was that if we have some mathematical model, we have to input the deterministic value of the input parameters, we will get the output parameter. However, the mathematical, even if the mathematical parameter we are very sure of is present the inputs may not be fixed, the inputs may not be precise. Okay, and this could be due to two basic reasons or two major reasons. First one is the natural reason, which is also known as aleatory variability, and second one is knowledge based reason, that is also known as epistemic uncertainties, which I will be discussing briefly in the coming slides. When I'm talking about aleatory variability, it is associated with the natural variability or inherent variability associated with the rock, and this is present due to random orientations of different types of mineral grains along the rocks. If I'm talking about this particular picture, and also there can be differently oriented discontinuities or randomly oriented discontinuities which are present along the rock in the form of intra and intergranular cracks. So you can see here the cracks could be along the grain boundaries also, and it could be passing through the mineral grains themselves. In both of these cases, these discontinuities are randomly oriented along the whole domain of the rock, which we have to deal with. And therefore, this inherent variability becomes an important part when we are estimating the properties of rocks. The best part is that when we are dealing with aleatory variability, actually, we can use some traditional stochastic model to handle this aleatory variability part. So the idea is that if we keep on testing, suppose if we want to estimate the UCS of intact rock, suppose, so what we generally do, we extract the samples from some of the locations or some of the boreholes from the site. We bring these samples in the laboratory, then we can test them in the lab. And based on some limited number of the testing, we can get some idea or some trend that what particular trend this UCS value of the rock is actually following. And based on that, we can assign some stochastic model to that. Okay, so therefore, the best part is that the aleatory variability can be handled using standard stochastic models. Okay, and this all of this variability which is existing, aleatory variability exists in the rock mass is due to the long thousands of years of formation history of any rock. Okay, in which it undergo several weathering cycles and associated or other destabilizing factors, because of which this random orientations of all these parameters takes place. So when we are dealing with aleatory variability, we are assuming that we are dealing with objective data. So what do we mean by objective data? So if I'm talking about UCS, so if we have the same samples, if I'm testing it in different laboratory as per standard guidelines, ISRM suggested guidelines, we should be getting the same value. Okay, so there are no personal feelings, opinions, or experiences associated with the laboratory testing when we are doing the UCS test. Similarly, when we are talking about elastic modulus, if we are following the standard procedure to find out the elastic modulus from the stress strain response of the intact rock, we should not be getting different result. So the basic idea is that if I'm taking a sample, the result, the output is completely free of the personal feelings, opinions, and experiences which we have, or any biases which we have. Okay, so once we get or once we test some number of samples in the laboratory, we can fit some probability model on the data using well-defined statistical methods. And one important thing is that even if you keep on testing the samples, suppose if you are testing 25 samples, 50 samples, 100 samples, the aleatory variability cannot be reduced to zero. The aleatory variability or the inherent variability will always be there. So you can see here for the preliminary investigation, if I have this distribution RAD1 based on some limited number of the test data. And if I keep on testing the data, more and more data I keep on testing, then I can reduce this variability. I can reduce this uncertainty, but it cannot be reduced to zero, or we cannot have a fixed value of any input parameter which we want to estimate. Okay, and you can see that how this variability can look in the field. So for very small scale of the rock picture which is available, you can see that how the jointing is actually completely different in the first picture as compared to the second picture. And in the schematic also, I tried to show that if you are taking a sample from different locations along the rock mass, like if you are taking the sample from A location, B location, C, D, E, you will be getting different values of the output which you want to estimate. Suppose if I'm going to estimate UCS, you will have different UCS value from the samples taken from different locations. The reasons are shown here. Okay. How to deal with this variability? So the best or the simplest part is to ignore it, which we generally do. Okay, so what we do, we test some samples, we find out the average value, and we use some deterministic mathematical model based on which we can actually find out the output response of any structure. Second one is method two is being conservative. We will take the least or the worst case scenario. If suppose if I'm talking about UCS of the rock, we will take the least UCS value which we have estimated from our samples. We will design our structure based on that least value of the UCS, and then it will be resisting everything. Okay, so if you are dealing, if you have that much money and money is not a problem, that you can go with it. Third one is using the observational method in which the measurements are in which what we do, we can have some preliminary design related to any structure, then we can keep on monitoring that particular structure, that how that structure is actually behaving. Okay, and based on that you can have subsequent designs if the structure is not performing up to the tolerable limit, and otherwise if everything is going fine, then you can carry on with that particular design. And the fourth one is quantifying uncertainty, which is more mathematical, which is slightly difficult and unconventional for the design engineers. And in this particular thing, method 4, you have to characterize the uncertainties in the inputs using probability or statistics, and then you can characterize or you can propagate those uncertainties of inputs to the outputs using some probabilistic or reliability methods. Okay. So if I'm talking about the traditional deterministic method, this is what we are dealing with. We have one input value or one value of any input. Suppose if I'm talking about shear strength parameter, I can use one value. We have this mathematical model in which, suppose if I'm talking about limit equilibrium, we have to consider the equilibrium of forces and moment. And you can get a single value of the factor of safety for the slope. So this is the simplest method which we generally use. In the reliability analysis, what we are doing, we have this variability of the input. We have to use the performance function. Based on that, you can have a distribution of the factor of safety instead of a fixed value of the factor of safety. And through that, you can find out that what is the probability of failure. So probability of failure, suppose for the factor of safety is defined as the probability of the factor of safety less than this target value. Okay, so this hashed portion shows you the probability, and that can be defined as probability of failure. Okay, so reliability analysis actually helps us to deal with the variability of the input properties. How do we perform this reliability analysis in geotechnical engineering? So we have to use two mathematical techniques. First one is statistics, in which we have to quantify the uncertainty associated with the input parameters, and then we have to use probability theory to find out the likelihood of specific events on the outputs, considering the quantified uncertainty of the inputs. So in geotechnical engineering, when we all are geotechnical engineers, I hope that most of the inputs are actually variable. If you test different number of samples, you will be getting different values. And this is the basic procedure which we follow in reliability analysis. We have real world. From that, we extract some of the data, and we mathematically try to model that data using histogram on which we can fit the probability function using some statistical techniques. Standard statistical techniques are there, chi-square test and KS test, AIC value test. And you can also find out the statistics of these parameters based on the tested data. Once we get this model, we can define a performance function. So suppose the performance function for the slope is factor of safety. Okay. Based on the target value, you can find out what are the risk and the consequences associated, and then you finally make the decision. Okay. If the design decision is not sufficient, or the stabilization measures suppose are not sufficient, then you have to repeat this whole process with some different amount of stabilization measures and all those things. Okay. So this is our main concern, epistemic uncertainty. So epistemic uncertainty actually comes into picture due to our insufficiency to collect the sufficient amount of high quality data. Okay. So it is not associated with the natural randomness or inherent randomness. The reason due to which this epistemic uncertainty comes into picture, could be classified into two major types. So first one is quantitative reasons. If we are testing the data as per standard, but we can't perform the sufficient amount of the test, we will be left with very limited amount of the data. So these reasons are actually known as quantitative reasons, or incompleteness or insufficiency of data. Second one is qualitative reasons. If we are using some subjective estimations, some empirical equations to find out any property, these qualitative reasons comes into picture in the epistemic uncertainty due to our incapability to get the exact value of any property. So suppose if I'm talking about deformation modulus in the rock, we generally use empirical equations based on intact rock elastic modulus and rock mass classification systems. So firstly, the empirical equation we are using is empirical by its name. Secondly, the parameter like rock mass classification system ratings like RMR or GSI, they involve many parameters which we have to estimate objectively or subjectively by the expert's opinion. So suppose if I'm talking about GSI, there is a chart and we have to just look at the rock. We have to identify that under which class of jointing it is coming into it can be classified, and what is the condition of discontinuity. So different experts can have different opinions. So this actually brings in the epistemic uncertainty associated with the qualitative reasons. And obtaining additional knowledge or obtaining additional information related to any property actually can reduce this epistemic uncertainty, unlike the aleatory variability. So you can see here this picture where we have this measured data in the first case, and again in the second case we have some measured data. You can see if the measured data is sufficient enough. So if there is no incompleteness or insufficiency of the data, you can have this precise stochastic model which can be fitted over this data. However, this is not the case with the second scenario, in which the measured data is very limited and you cannot fit a precise stochastic model onto this data. There can be other stochastic models also that can fit this data. So our concern is actually not related to the qualitative reasons, epistemic uncertainties associated with the qualitative reasons. We are here to deal with the uncertainties associated with the quantitative reasons. So we are assuming that we have some data, a very few data, but that data is objectively estimated and the data is of very high quality. High quality in the sense that they have been estimated using standard guidelines suggested in the literature, suggested in the codes. Okay, so while dealing with the unpredictability in the rock mechanics, so this is the standard procedure that we generally follow. We estimate some of the properties from the samples taken from the field, and we get the distribution of the input. We use some traditional reliability analysis like Monte Carlo simulation, first or second order reliability method, point estimate method. We can find out that what is the uncertainty in the output, and based on the allowable value of that response parameter, you can find out that what is the probability of failure. So this is the most ideal case which we can have in the traditional reliability analysis. However, we often deal with practical complexity and major challenges in the rock engineering. The availability of limited data in rock engineering is very frequent, is very often. The reason is that the testing on the rock mechanics actually requires significant cost, okay, and significant amount of money, and also we have to deal with the practical difficulties associated with the site preparation, sample collection, sample disturbances, scale effects, and all those things. So since we have limited data, whatever statistics of the data or whatever probability model you are fitting on that data, that could also be imprecise. Okay. And that will actually result in the imprecise estimation of the probability of failure, or reliability index or sensitivity indices, which we will be talking about later. So the problem which we are dealing with is that in this particular presentation is that if you don't have enough data even to get this probability model and the statistics of the input, then what to do? Okay, so we are assuming in the reliability analysis that we have sufficient data to get the precise probability model and the precise value of its parameters. But if we don't have those precise probability models and precise value of statistics, then what to do. Okay, so this is what we are dealing with. Okay, so we are not talking about any qualitative reasons of epistemic uncertainty. We are talking about quantitative reason of epistemic uncertainties. The most simplest way there, as I was telling you, there could be several other methods. So we are currently using Bayesian techniques. We are currently using non-stochastic models like convex modeling and interval analysis to deal with this issue of limited data. However, the most simplest method which we found that can be used to approximate the epistemic uncertainty related to the input and to propagate that epistemic uncertainty to the output could be to augment our traditional reliability analysis method or traditional sensitivity analysis method with the standard statistical techniques like bootstrapping or jackknifing. Okay, so what are these techniques, statistical techniques? So suppose we have some original sample with the n data points, 1 to n. So you can generate some dummy samples out of this original sample using bootstrapping or jackknifing. And you can treat these samples as the replacement of original samples itself. Okay, so if you keep on doing the sampling of the same sample size from the field, you can have different values of the parameters associated. But instead of doing that, you keep on reconstitute this original sample to get the bootstrap resamples or the jackknife resamples, through which actually you can estimate what are the uncertainties associated with the parameters of this particular input. Okay, suppose if I'm talking about mean, you can find out the mean of the input based on this original sample, but you can also find the mean based on the bootstrap sample or jackknife sample. So for the bootstrapping sample, you randomly pick any data points and you can do, and you have to do this with without replacement of the data point. Okay, so you can do it for like 10,000 times. So you will have 10,000 values of mean of this input. Based on that, you can find out the variation or uncertainty associated with the mean of this particular input. Something similar we do in jackknifing, where we get the dummy samples out of the original sample by ignoring or by uh, sequentially deleting one data point from the original sample. So we keep on deleting one data point from the sample, you will get a new sample of jackknife. But the size of the sample in the jackknife will be one less than this original sample. Once we get these samples, actually, you have to perform the same traditional reliability analysis using each of these samples, okay, or sensitivity analysis using each of these samples. And now you will be obtaining not a single value of reliability index, which you get in traditional reliability analysis, or a single value of sensitivity indices of any of the input, which we generally get in traditional sensitivity analysis method, but you will be dealing with a distribution of the probability of failure or a distribution of reliability index or the distribution of sensitivity indices, which I will be talking about in the next coming slide. So the basic assumption behind these methods, behind these statistical techniques is that if you keep on resample from the original sample itself, the estimation of the variability or the estimation of the uncertainty will be something similar if you are independently sampling out the samples from the field. So this is the basic idea behind these statistical techniques. And as I was telling you, there are different techniques, but this could be considered as the most easiest technique, as we have to just augment our traditional reliability or traditional sensitivity method with by replacing the original sample with these bootstrapped or jackknifed samples. Okay, I will show you the examples also. So we have we have carried out the stability analysis of two types of tunnel, that is shallow tunnel and deep tunnels in the rocks using this technique. So in the shallow tunnel, actually, we are dealing with an explicit performance function, that is plastic radius around the excavation. If we are excavating in a tunnel, there is a zone of yielding which forms, that is the plastic zone, and the wall displacement or the convergence of the tunnel walls inside. Okay, and if we are considering the rock mass to be as a material which is following Hooke-Brown strength criteria and using convergence confinement criteria to get the explicit expressions of plastic radius and the displacement in terms of the input rock mass properties. And these are readily available in the literature. So there is novelty associated with with these expressions which we are getting. We have obtained it from some standard books. As compared to this problem, we have to deal with very jointed or disintegrated type of the rock when we are talking about shallow tunnels. But as we go deep down, there is a possibility that the discontinuity or the quantity of the discontinuities keep on reducing and the rock mass quality keeps on improving as we go deep down. So therefore, in these type of problems where we are dealing with deep tunnels, actually, we have to deal with very less number of discontinuities, but with the intact rock type of rock mass at a particular location. So therefore, we cannot use this Hooke-Brown strength criteria associated with the rock mass, but we have to use some specialized strength criteria or strength models like cohesion weakening, friction strengthening continuum model, or damage initiation spelling limit, in which there is non-simultaneous mobilization of different strength components associated with the strength criteria. For the shallow tunnel, this was a problem that we were dealing with. So this is a shallow tunnel where it is subjected to a hydrostatic pressure of 8 MPa, and we are using CCM method, that is convergence confinement method. And we are assuming the material to be Hooke-Brown material, which is elastic, perfectly plastic. And we have two performance functions, plastic radius and wall, whose expressions are given here in terms of rock mass properties. So MB, SB are the parameters of Hooke-Brown strength criteria associated with the rock mass. EM is the deformation modulus. Okay. And this convergence confinement method we are actually using, and this method can be used to find out these parameters actually by using thick cylinder theory, okay, which we generally use in the, or which we generally study in the mechanics. So what we got related to the analysis is that when we are doing the resampling and we are estimating the statistics of the inputs, actually, we are getting the variability or the uncertainty associated with the statistics themselves. So if we are talking about the UCS, if I'm talking about the mean of the UCS, there is not a single value of the UCS, mean of the UCS, which you are actually getting from the original sample, but a complete range or complete variation is there. Okay, and this variation is actually quantifying it. This variation is actually showing that how much epistemic uncertainty is actually lying when we are estimating the statistics of the inputs. And something similar has happened to the standard deviation of the UCS, where instead of a single value which we can obtain from the original sample, we have the whole variation which is there due to the limited data availability. So for this problem, the amount of the data which was available was like 22 data points only. Okay, and when we try to propagate this epistemic uncertainty of the input statistics to the output, this is what we obtained. So what are we actually doing to get this probability distribution of the probability of failure is this. So for each of these samples, like bootstrap sample, once we get this bootstrap sample, we get the best fit model and the parameters associated with that best fit model. Based on that, we are generating some samples using Monte Carlo simulation based on the probability characteristics of this bootstrap sample. And we are finding out what is the probability of failure or reliability index. And we are doing it for all the reconstituted samples. So suppose for the bootstrap method, we have reconstituted samples. We have 10,000 reconstituted samples or resamples. So therefore, we will be getting some 10,000 values of the probability of failure. So ultimately, it is mathematically simpler method because we are using the traditional reliability method, but we have to repeat that process for all of the reconstituted samples which we are actually generating using bootstrap technique or jackknifing technique. So you can see here that instead of the probability of failure, we are actually dealing with the whole distribution of the probability of failure, which is due to the epistemic uncertainty associated with the statistics of the input parameters of the rock mass. Okay, these three curves are actually showing that if we are considering the uncertainty in both the model types, so you are fitting different models for different bootstrap or jackknifing resamples, uh, that could be the first case. The second case is that you have fixed the probability model based on your original sample, but you are considering the uncertainty associated with its parameter based on the different bootstrap samples. So you can see if we are ignoring the uncertainties associated with the parameters of the probability model, then the uncertainty is significantly underestimated as compared to the other two cases where we are considering the uncertainty in both the probability model and the parameters. And in the second case, we are ignoring the uncertainty associated with the distribution type, but we are considering the uncertainty associated with the model parameters. Okay. For the deep tunnels, actually, what we have done, we have used FLAG 2D CWFS continuum model, and the performance function are three. There are three performance functions. First one is the extent of this damage zone depth of this damage zone. Second one is the displacement of the roof. Third one is the displacement of the wall. Okay, the CWFS model is actually this is the basic idea of the CWFS model. Where non-simultaneous mobilization of the strength components uh, is taken into consideration. So if I'm talking about Mohr Coulomb strength criteria, what we generally assume in the traditional Mohr Coulomb strength criteria is that C and phi are mobilized at the initial strain level. But in the CWFS model, what we are assuming that as there is an increase in the plastic strain, actually the bond between the mineral grains keeps on degrading. Therefore, the cohesion value, which is or the cohesion which is due to the bonding which is present in between the mineral grain, keep on reducing before getting constant. And since there is a bond breakage, there will be the mobilization or there will be some motion along the mineral grains. The friction keeps on mobilizing before taking some constant value. These are the plastic strain values. This is for cohesion, this is for friction angle, at which the mobilized friction angle and the residual cohesion becomes constant. These type of problems are generally happens when the rock mass at the site is massive, in the terms that where the GSI value is exceeding like 65 or 70, and there are high in situ stress value which are present. However, the analysis remains more or less same, where we have to generate the bootstrap and jackknife samples of the input parameters of rock mass, and we have to estimate again the epistemic uncertainties associated with the statistics of those input parameters, and we have to estimate the uncertainty associated with the probability of failures. Okay, so this is what we are getting for deep tunnels. So suppose if I'm talking about UCS, again you can see that this is the fixed value of the standard deviation of UCS and the mean value of the UCS based on the original sample. And this variation is actually coming out due to the bootstrapping or jackknifing, which we are actually using. And once we try to propagate this uncertainty of the input statistics to the output, you can see that how the probability of failure is actually coming out. And you can see again that when we are ignoring the probability associated with the fitting of any probability model, we can see that there is little difference. But when we ignore the uncertainty associated with the parameters, you can see that how the uncertainty is significantly underestimated in the probability of failure. So we have extended this method to global sensitivity analysis of rock structures also. So when we deal with sensitivity analysis, it is an important technique to provide the importance ranking of inputs. So by importance ranking, we mean that we can find out that what properties are most important and what properties could be or what properties are non-sensitive to the outputs of interest. So this actually in turn helps us to have effective allotment of the available resources. So you can't do infinite number of in situ tests. So if you have available resources, you will use those resources to estimate the sensitive properties as compared to the non-sensitive inputs. And for mathematically, if you want to reduce the computational efforts in reliability and probability analysis, you can consider or you can ignore the uncertainties associated with the non-sensitive properties, but you can consider the uncertainties associated with the sensitive properties only. This will reduce the computational effort associated with the reliability or probability analysis. So when we deal with the sensitivity analysis, there are two basic sensitivity analysis methods which we generally use. First one is local sensitivity analysis method, in which we estimate the sensitivity of the input at a given point of the domain. In the global sensitivity analysis, we consider the random points along the whole input domain. So when we are estimating the sensitivity using global sensitivity analysis, that means that we are considering the points along the global domain of the inputs. And we have different techniques associated with the global sensitivity analysis. So the basic idea behind global sensitivity analysis technique is that you have some output related to the inputs. So if you're considering the uncertainty associated with the inputs, both, suppose if I'm talking about y is equal to x1 plus bx2, so there are two inputs. So if you're considering the inputs uncertainties associated with both of the inputs, you will be getting some statistic or PDF of the output corresponding to the uncertainty of both of the inputs. Okay. In the second case, if you want to find out what is the sensitivity of a particular input, so suppose if I want to find out what is the sensitivity of x1, so I will fix the value of the x1 and I will again find out the statistic of the output or the PDF of the output, and I will find out that what is the difference that is existing when I am fixing the value of x1 as compared to the case where I am taking the uncertainty of the input into consideration. So based on the type of parameter or type of statistic you are dealing with while estimating the global sensitivity analysis, you have different methods like variance-based Sobol's analysis method. If you are talking about the difference in the variance of the output, then you are talking about Sobol's variance method. If you are talking about the whole probability density function of the output, you will be talking about moment independent Borgonovo's GSA. So we have used Borgonovo's GSA. The reason is that it is talking about the complete PDF, but not about a single statistic. Okay, so therefore there will not be any loss in the information. The algorithm which we generally use is Monte Carlo simulation based subclass method. So I'm not getting into the mathematics of it, right? But the basic idea is that you have some probability density function which is being shown here, this f y of y. You can see here, this is the probability density function associated with the variance or the uncertainty of all of the inputs. And if I fix the value of xi to some value, what is the probability density function that we are getting? Then we quantify the differences which are existing in the probability density function for both of the cases, and that will tell you that how much sensitive the particular input is. So if the difference is significant, that means that the parameter is significantly affecting your output. Okay, so to quantify the sensitivity, we generally use this Borgonovo's sensitivity indices, which can be quantified something like this based on this Monte Carlo simulation subclass method. So if you are interested, I can share those details also with you, but I have not shown those mathematical details in this presentation. In this method also, you can see that we are using Monte Carlo simulation. Okay, in this method to find out the sensitivity indices, and to generate the Monte Carlo simulations, actually you need to know that what is the probability model associated with the inputs and what are the precise statistics associated with the probability or models of the inputs to get those realizations and then to perform this global sensitivity analysis for any input. So again, if they are not available, if any precise probability model or if any statistic of the probability model or any parameter of the probability model is not available, or if the data is not sufficient, then again there will be uncertainties associated with those probability models and the parameters, and then it is going to affect the sensitivity indices which we are estimating by assuming that the uh, statistic and the probability model estimated using limited data is accurate enough, but actually it is not. Okay. So again, we are using this resampling global sensitivity analysis method, where we have this original sample, we have reconstituted sample based on the bootstrap technique and jackknifing sample, as I was telling you. And considering each of these reconstituted sample as an independent sample, you can perform the Borgonovo's GSA as you do in the traditional Borgonovo's GSA calculation. You can find out the sensitivity analysis of any property, and you can do it for all the reconstituted samples in a similar way. Once you do it for all the reconstituted samples, actually, you will have a distribution of the sensitivity indices instead of a single value of sensitivity indices. And there will be statistics associated with the sensitivity indices, which we generally do not see in the rock mechanics and geotechnical engineering. We are habitual of using a single value or a fixed value of the sensitivity indices, based on which we find out that this is the rank of the parameters based on their sensitivity on the outputs of interest. But this is not the actual case. If the data available is not sufficient enough, then you can't have a single value of a precise value of a sensitivity indices. What we generally do, even on the limited data, actually we fit something. Okay, we fit some data, we fit some model, we find out those parameters based on those limited data, based on the available literature, based on the experts' opinion. So generally the distribution which we use for any property in geotechniques is log normal distribution. Okay, we just fit it. Okay, even if it is not fitting well, then we assume that the distribution is log normal distribution. We do our all our analysis, and we find out a single value of the sensitivity indices of any input. However, this is not always true. Okay, we can have different models that can fit our data better. Okay, and dealing with single sensitivity indices is actually supplying some additional information which was not originally available. So you have used your subjective judgment to fit a distribution over to your limited data, and this information was actually not available to you. So whatever analysis you are doing by assuming the statistics and the probability model estimated using limited data is accurate, and whatever analysis you are doing based on this assumption is actually problematic. So that is the whole idea behind this resampling global sensitivity analysis method. So we have performed this analysis for a rock tunnel, shallow tunnel again with the same performance function of displacement and the plastic radius. So we have done the sensitivity analysis only for the wall convergence, that is UI. Again, everything else is same. Like we have assumed the rock mass to be a Hooke Brown material, and the performance function have been derived using convergence confinement method. So all these details have been already explained and shared with you. So what do we want to find out? We want to find out that for this UI, actually, what are the sensitive parameters? So if I'm talking about EM, if I'm talking about this MB, SB, so you can see that there is a ratio RP upon R naught, which is here, which includes all the inputs related to the rock mass strength properties. So we have to find out that what are these sensitivity of the input parameters. And these rock mass properties are themselves the function of intact rock properties, which we generally estimate directly. So the intact rock properties are the parameters or the properties which we directly estimate using laboratory testing. So indirectly, if we can find out that what are the sensitivities of those intact rock parameters or rock mass classification rating, we are indirectly estimating the sensitivity of these strength parameters. Why we are estimating the sensitivity of intact rock parameters? Because you are actually measuring those parameters in the field. So you have to allocate the resources for the estimation of those parameters. You are not directly estimating the parameters associated with the rock mass, that is MB and SP. You can see here that instead of a single sensitivity, single value of the sensitivity indices, uh, we are having a distribution of the sensitivity indices, which we can see here. And now you cannot say that GSI is the most sensitive property, but if you are giving this statement, it will be with a particular probability value. So you have to say that GSI is the most sensitive property associated with this probability, or MI is the least sensitive property associated with this particular probability. So this is how you have to deal with the outputs of the resampling GSA. And we have also done one convergence study. So if we keep on increasing the sample size of the original sample, which we are estimating in the field, uh, then the sensitivity indices, which are being shown here, they try to converge towards a single value towards, or their uncertainty keeps on reducing. So you can see that for a sample size of 250, actually, the convergence of the sensitivity indices were obtained for all of the inputs which we are dealing with. However, the question is that can we estimate, or can we have 250 samples tested for UCS value, tested for elastic modulus and other properties? That is the biggest question that we have to practically deal with. So these studies have some practical implications that I want to discuss. So basically, right now, what we know about after this presentation is that our target is to get a precise and true value of a rock property, which is impossible to get. The reason are natural and knowledge-based reason. The true value of any property, or true and precise value of any property, correspond to the whole population of the rock domain. So which is not possible. Actually, we are dealing with meters of the rock domain in rock engineering, and it will be difficult to find out a precise or a single value of any property. So practically speaking, we cannot even estimate the aleatory variability because we have very limited number of the boreholes and drifts excavated at a site, from which, if we want to find out, suppose deformation modulus, if we want to find out using plate load test or plate jacking test, we generally do 10 to 15 tests at the max, and that too for large scale project. We do not do these type of tests. You can see here like plate jacking test, plate load test for small scale projects. Okay, and finally the result is that we are left with very few data associated with the rock mass properties. So the question is that whatever test results we are obtaining from here, could these test results represent the properties truly? As the test domain is significantly smaller, this test domain is only this drift, which is generally 1 or 2 at a particular site. as compared to the actual domain. So the ignored issue in the existing reliability or GSA method is that we are assuming that whatever statistics of a property we are getting from this limited data, like for 10 to 15 data, is correct. There is no problem associated with it. There is no epistemic uncertainty associated with it. And you can directly use them to find out your sensitivity indices or reliability indices. So this is the biggest problem associated with the traditional methods. So if we are talking about rock, so imprecision is often, that is what I was telling you. But the present method actually is telling you or is giving you the distribution of the stability, sensitivity indices or reliability indices instead of their fixed value. So at least you now know that what is the uncertainty associated, and then you can take decisions of testing more or of getting more data associated with the input properties. The major hindrance in the application of these methods is decision making. So ultimately, if you are performing any analysis in rock engineering or in soil engineering, anyone, the ultimate aim is to find out that whether your structure is stable or not. Okay, and this is the biggest problem associated with these resampling reliability or GSA methodology, which we are facing currently. The thing is that if we are talking about, suppose slope, if I'm talking about, or tunnel I'm talking about, if I'm doing a deterministic analysis, I have single value of input. So giving input is much easier. You'll be getting a single value of deformation, that is also much easier. And if you know the tolerable level or tolerable limit of the displacement, actually you can find out that whether your tunnel is stable or not. So decision making is much simpler in this case. This becomes more complex as you move forward towards the traditional reliability analysis, where you will have the distribution of the displacement instead of a single value. But in the tunnel engineering, in the rock engineering, actually, those allowable value of the probability of failures are also rarely available. But somehow there are some studies which tells you about the tolerable value of the probability of failure. However, in the resampling reliability method, you are getting the distribution of probability of failure. So now you will be dealing with probability of failure. So since there are not many studies available in the literature right now, we do not know that what could be that allowable level or allowable value of that probability of failure. So ultimate decision making, you have to use some of your subjective judgment. Okay. For GSA also, if you are using traditional GSA method, you are finding out the fixed sensitivity indices for any input, based on which you can actually rank the parameters or rank the inputs very easily. So you have a single value of sensitivity indices. In the increasing order, you can arrange them and you can find out that which one is the most sensitive property and which one is the least sensitive property with full confidence. Okay. However, for resampling GSA, you are estimating the distributions of overlapping sensitivity indices, which I was telling you right here. So we're getting the distributions of sensitivity indices, and these distributions are also overlapping. So you will have another probability associated with the distributions or the sensitivity indices or the importance ranking of the parameters. So this is a major hindrance when you are trying to use this particular methodology for practical field applications. We are working on it, but it may take some time. Okay. And further, the rock practitioners or designers with little background on the uncertainty quantification and probability theory might find it difficult to deal with or to interpret the results which we are getting. Okay. But an argument to support the impreciseness in the sensitivity indices or the reliability index or the probability of failure is that if a subjective decision cannot be made at the end, the level of knowledge is clearly insufficient to make a critical decision. For the decision making, it is better to know that the available information is insufficient for precise decision making instead of making wrong decisions. So at least you will be informed that you will need more data to get the precise or to get the converged value of the probability of failure, reliability index, or sensitivity indices. The major conclusions are that when we are talking about stability analysis of rock tunnels, we have to deal with aleatory variability and epistemic uncertainties both. And epistemic uncertainty is obtained in statistics of inputs due to data insufficiency. There can be other sources also, like qualitative reasons, which I was telling you. Coupled methods like jackknife for bootstrapping statistics with traditional reliability and GSA method could be a solution to reflect the effect of data insufficiency of inputs onto the statistics of output. And among the two resampling reliability technique, which I was telling you, jackknifing and bootstrapping, the results were actually very much overlapping. Okay. And the computational effort involved in the jackknifing is much smaller as compared to bootstrapping technique. The reason is that the number of reconstituted sample involved in jackknifing is much smaller as compared to the bootstrapping sampling, where you have to get the reconstituted samples in thousands. In the jackknife sample, you are dealing with the number of the samples with one less than the original size of the sample. Coupled method provides the distribution of reliability index and probability of failure instead of their fixed estimates, reflecting the effect of statistical uncertainty of rock properties. However, we are also comparing these methods. I mean, they are much mathematically very simpler, and anyone who is equipped with the basic probability theory and basic reliability theory can use it to have some idea. But we are actually in the stage, we have already communicated this work, but we are in the stage where we are verifying this technique or these tools with the Bayesian techniques and other non-stochastic techniques to find out that how much accurate they are, as they are mathematically much simpler. And if they are more accurate, then we can go ahead with these methods. And I am very thankful to all of you for listening to me. And I would like to thank my student Akshay, especially, who is working in this particular field where he has done the sensitivity analysis and the reliability analysis. And I would also like to thank one of my collaborator, Dr. Pandit Bharadwaj. He is an assistant professor in IIT BHU. We started our this work actually 3-4 years back, and now we are moving forward. Okay, so thank you so much. We have not gone up to that limit. We are dealing with the problems where we have random variables like 15 and like 3 or 4. Okay, but definitely we'll be exploring this. If we have random variables like more than 15 or 20, I mean, it should be, there should be some problem. Okay, the computational efficiency would be reduced significantly. But what we can do, I mean, one thing which can be done is that we can use some response surface methodologies where we have some explicit relation between inputs and outputs. So now we have advanced methods where we can relate many number of random variables to the output. So that will actually remove the calculation part in which we have to run the numerical simulations many times. So this is how we can deal with that issue. But we have not done any problem related to like these many random variables, like 15 variables. So we have to check it first. Yeah.